G'day, my name is Brendan. This is part 2 in a series of videos on mpstat, and I'm talking about mpstat for Solaris-based operating systems, including Solaris 10, Joint Smart OS, Illumos, and others. In this part, I'm going to go through all the fields of mpstat. In the first part, I went through 6, so I can skip over them quickly. The first was CPU, which is the CPU identifier. The second is MinF for minor faults. That's a normal part of operating system behavior. That can be when a thread has accessed a memory address that there is no mapping in the CPU's MMU, memory management unit, which may be because it has not allocated a physical page of memory to back that virtual page yet, because Solaris is a demand-based memory system. So seeing some degree of minor faults is normal, and that's how processors actually use memory. There are other reasons why you'll see minor faults as well, but it's a normal part of operating system behavior. Major faults is where a process accesses an address space which needs to go all the way to disk to be satisfied. That can happen because a process has mapped in an address space that it's then, from a file system file, that it's then accessing, and some of those accesses are causing disk I/O to satisfy them. We don't see too many major faults. Often files are accessed by processors using file descriptors where it's doing an open, it's doing reads, instead of mapping files in. So I don't expect to see that too high. It really depends on the application and the file system. I talked about CPU cross calls in the first part. Interrupts and interrupt threads. Interrupts is the rate of interrupts per CPU, and that happens when, for a number of reasons, which includes when devices need to tell the CPU or the operating system kernel that they have some work. For example, on this system, we do see a moderate rate of interrupts, and this is probably because the system is serving network I/O, and the network interfaces are interrupting the kernel when they've received a packet, so that the kernel's network device driver can then go and read that information off the network card. Interrupts, the example I just used, by the way, network interface cards don't always interrupt the kernel. For performance reasons, some of them will use polling mode versus interrupt mode. With polling mode, what they will do is coalesce several packets together, so long as it doesn't cross a timeout threshold, and then interrupt them together as a group. Especially these days with 10 gigabit Ethernet, you can have such a high amount of inbound packets that the interrupts would drown out a CPU. You'll actually see interrupts from cards light up CPUs, depending on the card, depending on the driver, but these often get mapped to a particular CPU. So I'm not at all surprised that CPUs 0 and 15 have a much higher rate of interrupts than the other CPUs. It will be because there's some physical device that's mapped to interrupting that CPU. I can use MDB. There's a D command called : interrupts to find out which device drivers or physical devices are interrupting those CPUs. And I can also use a dtrace-based tool called mpstat. Interrupt threads. This is how many interrupts were serviced by threads. Some of the interrupts are actually high priority interrupts that are non-blocking. If they have a certain interrupt priority level, they will come in, get processed, and then be done. They'll pin whatever thread is on CPU. And that's done for performance reasons, as well as the being able to have a guaranteed response time for a high priority interrupt that you need to get executed very quickly. Lower priority interrupts include, say, the network device I/O, and that's what this column is showing here. So again, this is very normal. Some of the higher priority interrupts versus lower priority interrupts, which are included in the INTR count. CSW is context switches, and ISCW is involuntary context switches. Context switches is a normal part of operating system behavior. That's where a thread is doing a blocking request or is voluntarily leaving CPU so that other software threads can come on and run. You'll see a lot of context switches for I/O-bound applications. So, for example, a web server that's doing a lot of network requests. It may also be doing disk I/O. And each time it does a read or a write that's blocking, it will context switch off CPU. Involuntary context switches happen when the kernel decides to context switch off a thread, not when it's decided to, but when the kernel has decided to. That can happen because you've hit 100% CPU utilization, and for a time-shared operating system, it needs to bump lower priority threads off CPU so that higher priority threads can run. The column CSW will include most, if not all, of the ISCSW column as well. So this column is not just voluntary context switches. This is all context switches that resulted in a thread leaving CPU and another thread starting. And then ICSW is mainly the preempt routine, but this is the involuntary context switch preemption by the kernel. Migrate is thread migrations. That's where a thread is running on one CPU and then is moved to another for whatever reason. The operating system may be balancing load. SMTX, I talked about in the first part, that spins on kernel mutexes. And SRW is the same, but for reader-writer locks. Syscalls is how many system calls were executed on the CPU. System calls are a normal part of application behavior. That's how a userland application requests to the CPU, to the kernel, sorry, to do work, to do privileged work. So high I/O bound applications, like in a web server, you'd expect to see a lot of system calls. User sys, wait and idle, I talked about in the first part. So that's a very quick rundown on the columns for mpstat. For more details on the columns, the man page is rather sparse, but you can read books including Solaris Performance and Tools, and especially Solaris Internals, which go through a lot of the fundamental operating system details for reference, especially minor faults, talking about how the locks work, how context switching works, interrupts. It's all in there. Thank you.